Hello, organic chemistry folks. So, I'm going to go a little bit farther in chapter 23. Probably not too far, but go a little bit further. Get started. I'll be sketching in back of one of my books. So, okay. We had talked about in last class about how to name amines. So, before we go on to any kind of reactions, any type of amine-based reactions, we need to discuss on the spectroscopic properties of them. So, mind you that primary and secondary amines can have intermolecular hydrogen bonds, but they tend to be less electronegative than OH bonds, so they're stronger. Well, less strong. So, NH2 combined with other things as opposed to all these guys can hydrogen bond, but not as strongly as our OH. In terms of the tertiary amines, they are, since they don't have any hydrogens attached to them, no hydrogen bonds. Comes to things like boiling points, they're going to have the lowest boiling points of those. They're even lower than, if I'm looking at functional groups with, we're going to talk about, we have tertiary amines, kinds of boiling points, lower than ethers, then primary / secondary amines, and then alcohols. All of course, similar masses when it comes to boiling point. So you're better to have ether than you are to have a tertiary amine. Remember, when we talk about spectroscopic rules, mass spec, a odd number of nitrogens means odd M plus dot peak. So the first peak you should see in the spectra is almost always even. Every fragmentations, all the fragmentations are odd. But the M plus peak should be even. But so if you have an odd M plus peak dot peak, then you'd have even fragmentations until you lost the nitrogen. So if we lose the nitrogen, we lose the thing that's making it odd, makes an odd thing even. If you subtract an odd from an odd, it becomes even. But if you subtract even from odd, it still stays even. It still stays odd. The first loss is always the thing. So, okay. That's the only thing you can really take away from in mass spec. You can figure out, oh, I have an odd number of nitrogens. But that usually means 1. But if you have 2, you're going to back to having even mass. So that kind of throws things off. So, like, this structure is going to be odd, but this structure is going to be even. 2 nitrogens. So, all we can figure out is the odd number of nitrogens. Now, in the IR, If it's primary or secondary, you're going to get an NH stretch. 3,300 to 3,500. If it's primary, you might even get 2 stretches. That's often the case. 2 stretches. That happens. You might get 2 stretches. That's not always a guarantee, but you're looking for that. Single OH, a single OH is only going to give 1 stretch, but a primary amine probably give you 2 stretches, so that's a big defining factor. Now, we don't really look for the CN stretch, so we won't worry about that. Now, protons, proton is very hard because with an NH bond, it could be anywhere from 0.5 to 5 ppm. It's very not downfield for very downfield, so it's not really that useful. The same thing, the CH adjacent to an N, it's like 2.3 to 3. We've said a lot of things. If it's adjacent to a functional group, it's probably between 2.3 and 3, something like that. It's not super useful. Even then, C13, not that useful. If it's if you have a carbon adjacent to a nitrogen, the carbon is somewhere between 30 and 50. It gets a boost, but it's not really a ton you can tell. Ideally, you'll know the biggest thing is, as I said, the IR and the mass spec gonna help you there. But okay, so when it comes to preparing amines, there's 2 main ways. Well, sorry, 3 main ways. There's 3 main ways when prepping amines. So, first one is nucleophilic substitution. And I'm going to go through each of these in depth. Well, not really in depth, but at least a little bit more than I'm going through right now. Number 2 is reduction of nitro groups. Nitro. And number 3 is called reductive amination. Amination. So it's slightly different from reducing the nitro groups, but it's still same idea of reducing. So condition 1, our nucleophilic substitution, is essentially an SN2 attack followed by deprotonation. Because, as we said, amines are good enough nucleophiles that they don't have to be charged. But once they bind, they need to be deprotonated in order to destabilized. Deprotonation. So like a simple replacement of a amine could be done. So like if I have Rx in excess and I throw in ammonia, first it's going to form RNH2 and HX. But then it's going to keep going and go to R2NH and R3N, and maybe even R4N plus X. That it can keep going. So we're often going to form a mixture of primary, secondary, and tertiary. The only reason why it would even stop at quaternary is because there's no more electrons to donate. It's no longer can act as any sort of Lewis base. So we're often going to get a mixture of these guys. So the only way to stop this, the only way to like isolate just one product is to limit the amount of amine. To control the amount of amine. So if we have amine in great excess, it stops it at after one addition. So if we have far more product, far more ammonia than we have of the halogen, it basically all of them get a chance to add once, and we still have some ammonia left over, and so it can't keep adding. But if the halide is in excess, the quaternary is the product. Quaternary ammonium is our byproduct. So it's just a matter of, well, once it adds the first time, it's going to keep adding, because once we go forward, it's easy to lose a proton. It's harder to lose like a carbocation. Carbocation is a less stable leaving group than our proton. So with that in mind, it's only going to go forward, not really backwards, which is why it's going to keep pushing forward. So here's a better way to form a primary amine that avoids the issue of having to very carefully control that. So this is called the Gabriel synthesis. It's synthesis, and it uses an acidic phthalimide. So this guy is a bicyclic system, 5-membered ring hooked into a 6-membered ring. This is fully aromatic right there. We have 2 ketones and an NH group right there. So a fully conjugated system, as you see. Right now, as it is, that is stable. But upon depronation, it becomes a very good nucleophile for SN2. So put some base in there, depronate that decomposes under basic hydrolysis to form the amine. So the basic reaction, the reaction that we're looking at, this is like when we used the NBS with our bromine as a way of carefully adding just a little bit of bromine. Well, we're going to use this to add just a little bit of ammonia. So, tack there, kick that off. We're going to form our basic amine, which is now a very good nucleophile. Because what do we say? If ammonia by itself is a good nucleophile, then now basic ammonia is even better. So this guy's going to then go on to swing over there, attack that, kick that off. So we're going to place that. Now we have R bound to the nitrogen. And one pair. Now, in the presence of more base and water, this is going to pronate and depronate that, and it's going to essentially break that apart into a dicarboxylate and ammonia. So once we've fully added this, we get our ammonia, but we also get the thalidomide going to break down into a dicarboxylate. The basic conditions and the water is going to assure that. So in this way, we can make sure that we only add the one time, because it's only going to add the one time, and it's that once we add the water, that's when it's going to break down. And so it only has one acidic proton, so it can only add one time. It doesn't, and not until we add enough water in there does it continue breaking down. Okay. Now, condition 2. Condition 2 is reduction of nitro groups. Reduction of nitro. Basically, nitro is not the hardest to do. We can do other reductions as well, but reduction of nitro groups, it's actually rather easy. We can do this under hydrogen and platinum conditions. Basically, platinum or palladium and carbon, basically the same hydrogenation that's going to reduce our alkenes down is going to reduce nitro. And that's going to just reduce it to ammonia. But we can use other ones, maybe a little bit easier. So, or we can use, say, iron with hydrochloric acid, or even tin with hydrochloric acid. Under these conditions, it'll just reduce no problem. So it's relatively easy. Don't forget, we can also reduce our nitriles. That nitriles can be reduced by using the strong reducing agent, lithium aluminum hydride, and then afterwards putting in water or acid and water. This will reduce that down into a primary amine, keeping that carbon in place. Don't forget that carbon. And with that in mind, remember that CN is a good nucleophile. So you can easily add an amine by first adding in a cyanide group and then reducing it. Adding the cyanide and reducing it. So it increases the chain by 1 before putting the amine in. So we can do SN2 addition with cyanide without much of a problem. And then you don't have to worry about the multiple additions as well. That's just one way. And one other way to do that is from an amide. Reductions of amide. And whether it's a primary, secondary, or tertiary amide is going to depend on whether it's a primary, secondary, or tertiary amine. And just that there, like if I have that's a tertiary amide, and I just use lithium aluminum hydride and acid, we're going to have a tertiary amide. Remember that this basically all that is that gets reduced, nothing else. With that in mind, reductive amination. So reductive amination is our third and final types of ways we have to prepare amines. So reductive amination. So this one is we use this one is we're going to convert carbonyls to imines and then reduce. So this one requires us to recall some of the reactions we had when we did carbonyl reactions. We talked about, under these conditions, the nitrogen is going to replace the oxygen. So like if I have that and I add in HNR2, the byproduct ended up being NR2. That was our imine. And then when we put in something like sodium borohydride, let's see. Sodium borohydride. I think that's right. We can then just reduce that down to back to an amine. So that's one possibility. Wait, oh, my bad. Okay, so that should be plus. That's tertiary amine. Or alternatively, oh, sorry, my bad. This guy, you needed sodium cyanoborohydride. This one, I thought it was a typo, but now reading my notes again, this is sodium cyanoborohydride. They're saying that this is a particularly effective reducing agent for this. Basically, the sodium borohydride, the cyano group is pulling electron density further out of the boron, maybe further weakening it, and make sure we only add in the hydrogens we need to. But here's another one. Quick reminder, like, if I had another ketone that was attack with, this was a secondary. What happens if I attack with, say, say that's a tertiary amine. What? No, that'd be a secondary. I attack with a primary amine. Attacked with a primary amine instead of a secondary amine. This ended up as that amine, and then using the reducing agent, sodium cyanoborohydride, we would get a secondary amine. Sorry, let me adjust that. That essentially in this way by adding an amine onto a ketone or an aldehyde, we are able to replace the carbonyl oxygen with an amine. And the number of carbons bound to that amine is going to depend on what amine attacking group we have. So that is some of the ways we can prepare amines. All of these ways are ways that we've already kind of covered in the past. So none of these are particularly novel, but it's always good to have a good refresher. Okay, with that in mind. So here's a few reaction features and general rules. When it comes to reaction features, if we look at this, comparing N, O, and F, we have just general basicity and nucleophilicity. That amines will act. Amines will act as an acid. Will act as bases on acidic pHs. So basically, amines will. Let's start again. Amines will be bases when there's acidic hydrogens. Be bases with hydrogens, and there'll be nucleophiles with electrophilic carbons. So it all depends on the conditions. If you carbons. Sorry, with electrophilic carbons. It all depends on what we have. Remember our lines. If you put carboxylic acid, it might depronate it. If you put like a diketone, a beta diketone, it might depronate it. But it might also attack one of the carbonyls. So it all depends. To be a base, here we go. To be a base, base will need we need a pKa of greater than 10. pKa of less than 10 on the acid. So if the acid is greater than 10, no. And that has to do because our amines, our protonated amines, have a pKa of approximately 10 to 11. So we always need the acidic proton to be of lower pH. So if it's not below 10, it's not acidic enough to pronate ammonia. So what does that mean? If we look back at our dicarbonyls, carbonyl chemistry, what do we have? Let's see. Let's look at that. Acidic ketones, no, not going to depronate alpha carbonyl on a ketone, nor aldehyde. Not a diester. Maybe a dinitrile, maybe a ketoester, possibly a beta diketone. A beta diketone, according to my notes, is 9. A pKa of 9. But that's pretty much the limit. You're going to get, which is just a quick reminder. So we have this guy is 9. That guy is 10.7. This guy is 11, pH 11, 1. So this one's maybe the only one likely to be deprotonated, if at all. Your carboxylic acids, that's closer to pH 4.8. Your alcohols, that's closer to 16. So the likelihood of you deprotonating any of these guys, no, not very likely. So, but acidity and basicity can be used to change the polarity and water solubility for extraction. Basically, any factor that will increase the electron density on nitrogen will increase the basicity of nitrogen, and vice versa. So any electron donating groups on the nitrogen means it's going to be more basic. Any electron withdrawing groups is going to make it more acidic. So in terms of, alkylamines means it's going to be greater than a normal amine due to electron density. Donating. So a secondary or tertiary amine will be more basic than a primary amine. And that might be why, one more reason why primary amines, but then why it didn't want to stop reacting when in the presence of the alkyl halide, because the alkyl amine was a better nucleophile than the regular ammonia, and the secondary amine was a better nucleophile than the primary amine, and the tertiary amine is a better nucleophile than the secondary amine. And so we're pushing more and more electron density on the amine, it's more likely to attack. Aniline, for example, is weaker than amine because of because of delocalization. So remember, aniline is, so we can draw resonance structures that it has a positive charge here, but the fact that I can delocalize this at all means I'm pulling electron density out of that nitrogen. So, but then we'd have amide. We have in terms of carbonyl, amide, and then we have much, much greater to amine in terms to basicity due to delocalization. That delocalization. That pronation will, and we're talking about in this case pronation occurring on the oxygen. But the pronation occurs on the oxygen in the amide rather than on the amine. Quick reminder, we talked about this earlier. The basicity of heterocycles depends on whether that lone pair is used in making it aromatic. And this basicity will also determine the hybridization. So, I'll give some examples. This group, or the lone. I'm going to redraw that. Okay, let's redraw that so it's not looking super janky. That this lone pair is not used in making this aromatic, and so that's basic. This lone pair is going to be used to make this aromatic, so that's not basic, because we have 1, 2, 3, 4, 5, 6, as opposed to 1, 2, 3, 4, 5, 6. And so, as I was saying, that the hybridization also controls it. If it's a sp2, it's going to be a weaker base than sp3 because the sp2 holds the lone pair more tightly. Pair closer to the the nucleus. Because I know this is kind of hard to imagine, but remember when we're having these hybrid orbitals, they are made of some proportion of the s orbital, which is the sphere, and some portion of the p orbital, which is the lobes. They're a little bit longer and wider. Well, sp2 is made out of 2 p orbitals and 1 s orbital, so it's 33% s. sp3 is made out of 3 p and 1 s, so it's 25% s. And less s means that is less tightly held to the nucleus. So there's many different ways you can make an amine more or less basic. But I will go ahead and stop there. I know that's not very far, but I'm going to leave it at right there and not push this too far, because I know these lectures like this are not always ideal.